Hello, welcome to a continuation of the Henstitute. This is for AP Physics 2. We are now going to talk about Archimedes' Principle here. And you may have learned about Archimedes sometime in the past, whether it's in another science course or just heard about him. Archimedes is an ancient Greek philosopher. He's known for creating a variety of different inventions, but probably the biggest one is that he supposedly took a bath and he dipped himself into the bath and realized that the amount of water that spilled out was equal to his volume, and then jumped out of the bath and said, "Eureka," and went out. Archimedes' principle uses that concept, but it's not actually that concept itself. I put this little world up here. I've linked it to a TED Ed video. I'm going to put that on as well. It gives a good idea of a potential of what may have happened with Archimedes in terms of that. But Archimedes' principle itself deals with this idea of a buoyant force. And so a force that's actually going to push up on an object when it's either partially or completely submerged in a fluid. And the basic idea is that this buoyant force is equal to the weight of the fluid that has been displaced. And so that's why this idea of water displacement was very important for Archimedes. But the equation pretty much boils down to something very simple like this, that the buoyant force is equal to the weight of the displaced fluid. And going into how we find weight, we'll be dealing with that, because we know that the weight of an object is equal to mass times gravity. But if we're talking about a fluid, we're actually going to combine the idea of density that we just got done talking about. And so we rearrange this. The mass of an object is equal to the density of an object times its volume, and then we substitute this in. So we're actually going to find that to find the weight of a fluid, it's actually going to be often easier to take the density of the fluid times the volume of the fluid times the acceleration of gravity. And I always like to write it like this because I think rho, which stands for density, and the g for gravity kind of mirror each other around the volume. Now, you don't actually have to do this just for a fluid. It could be for any object. If you know the density of the object, the volume of the object, and gravity, this is another way of finding the weight of that. So the idea, this first picture over here, is showing that if I take this 100 Newton object and I put it in the water, there's going to be some buoyant force because it's displacing some of the water. And then if we actually have something float, what's happening is the buoyant force and the weight of the object are equal to. So the buoyant force is always equal to the weight of the displaced fluid. But if it's going to float, then that buoyant force is going to equal the weight of the object itself. So we're going to use that to try to solve a problem. So let's say we have some raft and it's out in the water and it's made out of yellow pine wood. So that's going to be very important because we go back, we had this little one. We know that yellow pine wood has a density of 550 kilograms per cubic meter. So we're going to keep that in mind. Go forward again. So I'm going to write that down just as extra information. The density of the wood is going to be 550 kilograms per cubic meter. It's floating in the water, so the density of our water, our fluid here. And fluids are basically anything that is not a solid. So it could be a liquid or a gas. We tend to think of things like water and liquids as fluids, but gases are also treated as fluids. But our density of our water fluid here is 1,000 kilograms per cubic meter. And like I mentioned, that's something you're just going to have to kind of get used to. So we're trying to determine a couple of things. If this raft floats, and then if it does, how much of it is actually in the water itself. So we start out, we have the different dimensions of this raft. It is 0.3 meters deep. It's a 4 meter by 4 meter raft. So it's basically a big rectangular solid. So what we're trying to figure out is if the weight of the raft and the buoyant force on it are equal, or what exactly is going on. So to start off with, let's find the volume of the raft itself. So I took the length of the raft times the width of the raft times the depth or the height of the raft. So length times width times height gives us that the volume of the entire raft is 4.8 meters. And so if I want to figure out what the maximum buoyant force is, in other words, if the entire raft was in the water and it displaced that entire volume of water, so if it displaced an entire of 4.8 meters, how much buoyant force would be on it? Well, the density would be 1,000. And then our gravity here would be our 9.8 meters per second squared. So I multiply those three things together, and this would be my maximum buoyant force. So if the entire raft was underneath the water, the product of those three different things, pull out my handy dandy calculator. Come on, calculator. So I take 1,000 times 4.8 times 9.8. And we get 47,040. 47,040 newtons of force. So that's if we got the entire raft in the water. This is how much that it would actually be pushed up with. But how much does the raft itself actually weigh? So normally to find the weight of the raft, I would take the mass of the raft times gravity, but I don't know the mass of the raft. I just know the dimensions and I know what it's made out of. So what I did is I'm going to use the exact same equation. I'm going to take the density of the pine wood and the volume of the raft times gravity. So the density of the pine wood was 550. The volume of the raft was 4.8 meters. And then gravity is just our 9.8. So if I take these, 550 times 4.8 times 9.8, and we get that this is 25,872 newtons. So the question is, does this raft float? And if the raft is floating, then this has to be smaller than this. And sure enough it is, since the maximum, this is actually smaller than the maximum buoyant force, this thing is going to float. Now, a lot of you probably figured that out without doing the calculations I did, because you said, hey, I remember learning in a science class that if the density of an object is smaller than the density of the stuff it's floating in, that it would float. So that is true. You know that 550 kilograms per cubic meter is smaller than 1,000, therefore this raft should float. So you are totally correct. That is another way to do it. Just look at densities and we'd have it figured out. I'm going to actually show you that the densities are going to be the most important a little bit later, so just kind of keep that in mind. So now my last step is, how do I figure out how much of it is actually in the water? So we know the weight of the raft. We actually have that value, this 25,872. And then for our buoyant force over here, this is going to be the density of the fluid. So this is going to be the density of the water. And that's going to be the volume of the raft that's actually in the water. So this is going to be the volume of the displaced water, and then multiply by gravity. Let's move this out of the way. So here's actually one way to kind of think of this, is I know these two dimensions, the 4 by 4 dimensions of it, that entire piece is in the water. And if you kind of look, what's happening, it's really just this little thickness that's important. So the amount that's actually in the water is what's being displaced. So what this is going to equal is the 1,000 kilograms per cubic meter. For this is going to be the dimensions. This is going to be a 4 by 4. So that's the area of the raft. And then it's going to be the H depth that's actually in the water. So this little H that's being pushed into the water, and then good old gravity over here. So what we're going to try to do is figure out how much of this is actually in the water by setting this equal to this. So the idea is if I multiply everything out and then divide it over, we should be able to figure out what H is. which is going to be the amount of raft that's actually in the water itself. Pull out my handy dandy calculator here again. So I've already got this number. Basically what I'm going to do is I'm just going to slowly kind of divide it by these different numbers just to make it easy on myself. So I'll start out, I'll divide it by 1,000. That changes it to that number. And then I'm going to divide it by 4. Changes it to that number. I'll divide it by another 4. And then last but not least, I'll divide it by a 9.8. So what I did is I kind of chopped it away and just kind of divided everything over. Most of you would probably multiply the 9.8 times 4 times 4 times 1,000, get a number and divide the whole thing over, and you should be good. And what I get is 0.165. What that means is there is 0.165 meters of raft in the water. So the amount that's actually in the water is 0.165, a little bit more than half of the entire depth of this raft. And there you have it, applying Archimedes Principle. Archimedes Principle just deals with this idea of how do you find a buoyant force. And buoyant forces are the weight of your displaced fluid. Now, one last little thing that I think is kind of neat about this. If you go to this concept, the weight of the raft being equal to the weight of the displaced fluid and trying to determine if things are floating, if I go to how I found the weight of the raft, so I'm going to grab this part real quick. This is just a little addition. So the weight of the raft, and then our buoyant force, which is really the weight of the displaced fluid. What I end up with is this would be the density of the wood, so the density of the raft, times the volume of the raft, times gravity. And then over here, this was the density of our fluid, so this was our water, times the volume of the displaced fluid, times gravity. One of the things I think is kind of neat, setting these equal to each other, you will notice that the acceleration of gravity is irrelevant. If I were to take this raft and float it in a swimming pool that was on the moon where gravity is actually less, it would float exactly the same. So it wouldn't matter what the acceleration of gravity is. Then, like I was saying, we know that since the density of the wood is smaller than the density of the fluid, that kind of relates things. What it's basically kind of boils down to is if you take the density times the volume of one thing equal the density times the volume of the other thing, this is actually another way to kind of go about it. So we could actually find like a percentage if I bring this density of the fluid over. So I'll take the density of the wood, which is our raft, divided by the density of our fluid, and then the volume of the raft itself. This would equal the volume of your displaced fluid. So basically what we're saying is there's a ratio, the ratio of the densities multiplied by the original volume will tell us how much volume is actually being displaced. So since we knew the volume of the raft, we could, and the densities of the raft and the fluid, we could actually find how much volume of water would need to happen. And if this ratio was greater than 1, obviously it doesn't float, but this is kind of goes back to things that you were talking about before. Hope you enjoyed this edition of the Henstitute, and we will have more fun throughout the year. Take care.